Right, these are our electrical power things, right? So if we've got a alternating current, right, it's going to be this this is our voltage. This could be our voltage or our current, right? Our peak voltage is this, so that's our V peak, right? But what this says is if you want to get the average voltage to use for power, take the peak voltage and divide by square root of 2. When I was taking like Navy, electronics things, they simplified it. They said, oh, just multiply by 0.707, right? Which is 1 over the square root of 2. Okay, so what this does is it makes it so that it's the average of that, right? The same is true for the current, right? If you want to calculate power, this is for power, right? Okay, take the current, divide by the square root of 2. That's kind of like an average that you would use, right? Remember that voltmeters will give you RMS unless you tell them otherwise, okay? This just says, all they're saying is that Ohm's law is obeyed, and it's best to say that this is for a piece of wire, okay, that doesn't have a lot of inductance, okay, that we can do voltage divided by current, okay? And it works for peak voltage, it also works for RMS, so this is just Ohm's law. Right, the power max is, of course, the peak current, which happens at the same time as the peak voltage if there's, again, no capacitance or inductance, so they're keeping it really simple here, okay? That's the maximum power, right? And then if you look at this, right, the average power is half the peak power, right? Now you can actually get that, obviously the actual power would be VRMS, IRMS. So these equations come from this notion, okay? So the average power, this is the average power, right, is V peak over the square root of 2 times I peak over the square root of 2. There's no plus, okay? And notice that the average power is I naught V naught over 2. There it is. Yeah. Right, and then this is our favorite transformer equation, right? So we've got the core, like this, right? Wangy, right? We've got here we have the number of primary windings, right? Here's our secondary, right? The symbol for transformers looks like this too, right? Here's the number of secondaries. We've got a voltage on the secondary. We've got a voltage on the primary, a current in the primary, right? A current in the secondary, right? And what they're saying, the most important thing is that because n is part of, I guess we don't have that equation, right? Because the Faraday's equation says that it's negative n change in flux over change in time, right? Okay, because the n is directly proportional to the EMF, you can just set up a proportion, okay? They all share the same flux because it's the same piece of iron, and we just set this up. So if you have fewer windings, let's say this is 100 volts, if this is, whoops, that's 1,000. If this is 100 volts, that's fewer windings, so maybe this is only 30 volts or something like that, right? It steps it down, it's proportional to it, right? And then they show that, somewhat paradoxically and nonsensically, that the current is inversely proportional to the number of windings. I actually much prefer that you do this, that you say I primary, V primary, that is the power going in, the power in equals the power out, which is I secondary, V secondary, right? I don't know why they didn't do that, or why, I don't know. I mean, just, it's not my favorite because it makes you just think about this the way robots would think about it and not really understand. This is energy, this is conservation of energy. Okay, understand that, this is for 100% efficient transformer, right? Okay, and then the final thing that they're not really talking about here is that we need to talk about I squared R loss, right? So if you've got a power line that has some resistance, the power lost by it is I squared R, right? And so what you do is you transmit the power at a really high voltage. You make the voltage super high so the current's super low. So when you plug it in there and get the power lost by the line, which is I squared R loss, the power lost is really small because they don't get paid for the power that doesn't make it to people's meters, which is why they transmit across the country, in long distances, it's super high voltage, like 500,000 volts, right? It's not cheap to insulate against that. But they do that so that they have very small I²R loss. It's a bit like making sure railroads have the perfect grade to them, You save energy in the long run. Anyway, yeah, hope that helps.